Hello everyone, and thank you, Roberto, for the introduction. And so let me just recap what we did last time very quickly, and I'll come back to the lecture notes. So we're looking at community detection. Right, so last class I tried to motivate the problem with some applied issues, applied problems where finding communities in networks is important. And then I focus on the stochastic block model, which is the most popular model in statistics for studying this problem. And this allows us to quantify things and measure how good the community detection methods are going to perform. I talk a little bit about statistical inference for the SVM. And most of what I talked last time was based on methods that cannot be computed. For example, if we have the likelihood, we cannot estimate the maximum likelihood estimator of the communities in the model because there are too many parameters, so we would have to optimize over a combinatorial space, which is not feasible, right? So this is, in some sense, unsatisfying that we cannot just simply use the classical techniques. And basically, what I have covered so far is limited in that sense. But I also mentioned a little bit spectral methods, which is what I'm going to focus on today in a more general way. And I also mentioned information theoretic limits. Which basically tell us when can we actually solve the problem, or when we have some hope of solving the problem according to the parameters of the model. And again, this is based on methods that cannot be computed. But today I'm mostly going to focus on spectral methods. I'm not going to talk about the theory. So, today is my last day in the course, but I will leave Joshua to continue going deeper into spectral methods and all the theory of spectral methods. So I encourage you to continue attending the lectures. So basically, one nice feature of spectral methods is that they can achieve the information theoretic limits under some settings. In particular, in the setting that I described last time, there are spectral methods that can actually do perfect clustering up to the limit of the parameters at which point no other method can achieve the same accuracy, right? So basically, in some sense, that's encouraging that we have some method which we can actually compute from the data. We don't need to optimize over a very difficult space with spectral methods, and we can get accurate community detection. But okay, let me see. Okay, so so before talking about spectral methods and linking the spectral method to the SVM, I'm going to review some of the ideas that kids cover in the first week of the mini course, which is basically latent space models. This gives a more general class of models that can be used to incorporate community structure, and then we will see later that some of the models that we have been talking about are actually special cases of this model, and this will allow us to link the ideas of the spectral methods with inference for some particular models with community structure. So the general definition of a latent space model is that we're going to have latent positions x1 to xn, which are going to denote some coordinates for each node in some latent space of dimension d. So I mean, d is a number much smaller than n. But basically, the point of these models is that we're going to represent the information contained in a node by a latent position. And then the probability that two nodes connect, so the probability that the adjacency matrix is equal to 1, is a function of the interaction between these two latent positions. And this interaction is measured as a function of xi and xj, Well, there are two functions here. The idea being that one of the functions, kappa, measures some sort of similarity or dissimilarity between the two latent positions. So for example, if the two latent positions are closer in the space, it's more likely that the two nodes are going to form an edge. And we can measure how we're going to quantify this distance or this similarity or dissimilarity in some way with kappa. And then sigma is just a link function, which we use for modeling the probabilities of this random variable. We have many options that we can use. But I mean, this is sort of like the most general version of the model. This was introduced by Hope et al. In 2002. And well, essentially, this gives a very general class of models that we can use to study network data. And I mean, one nice feature here, as I mentioned, is in networks, we typically don't observe information about the nodes. We only have interactions between different nodes, but we don't have any particular information about a given node. The idea of the latent space model is that we're going to imagine that there's actually some information encoded somewhere. We don't have access to it in principle, but this information is basically what we would have as covariates. For example, if we observe tabular data in classical statistics, we get a lot of features for each individual. So the idea here is that these latent positions are encoding those features for that particular individual, right? And we're going to represent those in a matrix X of size n by d, which in this matrix is encoding all this information in the networks. And by the way, I forgot to mention, but I sent a link to Roberto with the slides, so he will send it to everyone later. I will also put them on my website, but I was having some issues on updating it this morning, so I will do that in the afternoon. But yeah. Anyway, so that's the general idea of the model. As I mentioned, there are these two functions. I'm not going to go very deep on this, but basically, for the function sigma, we need to define some link function for the data. We can either use the identity, which is actually what we're going to use today. So sigma is just equal to sigma of y is just equal to y. And in this case, it's like a linear function where basically whatever we have here is going to be the output. We can also use logistic if we want to be more formal with the statistics to make sure that the probabilities are not bigger than 1 or smaller than 0. But I mean, in principle, we have many choices. And similarly for the dissimilarities or similarity functions, right? So we can encode the distance between latent positions and measure this with kappa. So if the latent positions are farther away, the probability is going to decrease or increase. Or we can measure inner products between latent positions with the idea that if two nodes are close in a space, they are going to have a small angle, and then that's going to increase the likelihood that these two nodes connect. Right? So I mean, these are some of the ideas that we can use. So, I mean, we can think of others, but this is just to illustrate the parameters of the model. So this is the general framework, but well, something important on the problem that we want to solve today is that, I mean, in principle, we have data, right? We have a network, A, and we have models, right? So we're going to say that P is the model for the network, right? So, I mean, we can use the models to assume some generating mechanism for the network, but in statistics, we want to go the other way. We want to do a statistical inference in such a way that we observe the network and we want to estimate the parameters. So, as I mentioned at the beginning of the lecture, the main issue with classical statistical tools is that we typically cannot compute the estimators very efficiently, right? We need to optimize over a very large space. So the methods that we want to use here are, well, basically we want to use efficient methods that allow us to go from A to P, and in particular, today I'm going to focus on the spectral methods. But in order to be able to do this connection, we need to choose an appropriate set of models that allow us to go from A to P, right? I mean, in principle, we can define an arbitrary model, but there's not a hope in general that we're going to be able to fit a spectral method or other efficient method for that model. But if we choose the parameters appropriately, we can get models for which spectral methods are a natural option to estimate the parameters. And at the same time, we want models that are general enough to cover different aspects of network data. So, I mean, we want a very large class of models, but restricted to the fact that we want efficient inference, right? So, I mean, in principle, latent space models give us a very large class of models, but now we just want to restrict to the ones that allow us to do inference with spectral methods. And that's the idea of the random dot product graph. So in the random dot product graph, we have a latent space model with x1 to extend the latent positions of the nodes. But we're going to assume that the link function and the dissimilarity function is going to be equal to the identity, right? And the dot product between the graphs, right? So, I mean, this is maybe the simplest latent space model that we can think of, but Keith already mentioned some of the ideas that basically we can efficiently estimate the latent positions of this model by looking at the spectral decompositions of the adjacency matrix. So that's basically the motivation for working with the RDPG model. So basically, yeah. So this is an identity link function and a dot product kernel. So that's the idea. An alternative definition that I'm not going to focus too much on it today. Maybe, I don't know if Joshua will talk more about this one. Well, anyway, but I mean, in principle, we can define the latent positions with a random distribution. So let's say they come from some distribution F, and we can define the model in a similar way. But I'm going to skip this because we won't really use this model too much. But anyway, so here's some intuition on the idea behind the latent space model. So we basically assign points to each node. They are represented in some latent space. Here we have a latent space of dimension 3. And then we measure, well, the angle, which is encoded in the dot product, but also the magnitude of these vectors. And depending on those, we're going to generate probabilities. So the probabilities are going to be inner products between these latent positions. We can encode it in a probability matrix, and then we can generate a network from it by sampling each of these nodes independently at random with these probabilities, right? But our goal is to go the other way. We have the network, some zeros and ones, and we want to estimate the latent positions X and the probability matrix P, right? So we want to go this route. Okay. So one limitation of this model is that, in principle, we can only represent assortative structures in the sense that nodes that are more similar are going to be connected with higher probability. And this is good in many settings, right? Typically, what we see is that people with more similar features are more likely to be connected in a social network or other things. But in some settings, we also want to represent the opposite behavior of this assortative structure. Sometimes nodes that have more similar features are less likely to be connected. Think of it, for example, in dating networks. People from the same gender typically date more people from the other gender, right? So in that sense, we also want to extend this model to allow for this type of disassortative behavior. And there's a very simple idea to extend that. Keith already mentioned this as well, but just as a reminder. So basically, what we can do is incorporate the matrix between the inner product of these two vectors. Let's say we have X and Y. We incorporate a diagonal matrix. So if this diagonal matrix has only ones, we recover the same random dot product graph model, right? So essentially, X transpose I, Y is going to be just X transpose Y, if this matrix is just the identity, and then the model is the same. But what we can do is incorporate negative signs on the diagonal of this matrix in order to allow for some of these dimensions to be disassortative. So basically, with this representation, we're going to, let's say D is equal to P plus Q, where P is the number of ones and Q is the number of negative ones. So we're going to have P dimensions that are assortative or are representing variables that make people more likely to connect, and Q dimensions or D minus P dimensions that are disassortative. So these ones make people less likely to connect, right? Yes.
Somehow you have to make sure that these are always between 0 and 1.
Right. Yeah, that's a great point. And I mean, from the model perspective, I mean, we can just define them in such a way that we make that constraint. There are some particular issues when we go the other way, because in some cases we may get estimates that are not exactly in that region. But I mean, as long as we have consistent estimates, that shouldn't be a big problem. But in some cases, it may be a practical issue. But for the problems that I'm going to talk about today, we don't really need to make sure that the estimates are between 0 and 1. Like, for example, for community detection, we only care about the cluster, so those issues don't happen. But yeah, that's an important issue. And that's part of the price that we need to pay for working with a livelihood like this, right? I mean, if we enforce some sort of like logistic loss or logistic link function, then we wouldn't have that issue, but that would make inference harder. But yeah, that's a good point here. Well, I mean, in principle, when we define the model, we can just make sure that everything is between 0 and 1 in order to make sure that these are probabilities. Okay, so that's how we define it. So yeah, so this idea was introduced in a paper by Rubin Delanchi et al., including Joshua, who was one of the authors of this paper. So yeah, basically with this idea, we can extend the RDPG model to any arbitrary low-rank structure on the adjacency matrix, well, on the probability matrix P that generates the adjacency matrix, which gives a very large class of models. I mean, there are some particular issues that one needs to pay attention with the generalized RDPG instead of the RDPG, but for the purpose of this lecture, I'm going to ignore those issues. I'm not going to focus too much on the generalized RDPG. If you want to read more about it, you can look at the paper and find the particular issues that arise, but we're going to ignore those today. And yeah, so, well, this is the formal definition. I mean, essentially it's the same thing, but we need to introduce this diagonal matrix in the middle in order to allow for assortative and disassortative dimensions in the model. Okay. There's some non-identifiability, and here the non-identifiability is a little bit more problematic than in the SVM. In the SVM, we have non-identifiability that we can switch the communities, and then we recover the same model, but I mean, we don't really care about the community labels. In the RDPG model, we have non-identifiability up to an orthogonal matrix. So if we have our model P equals X transpose, where X is the matrix of latent positions, we can incorporate the matrix in the middle here, W, an orthogonal matrix. It's basically going to rotate the latent positions or reflect the latent positions in some way, and that's not going to affect the probabilities of the model. You can think intuitively what this matrix is doing. We have this space of latent positions. We can rotate the latent positions, but the relative distances or the relative inner products between different nodes are not going to change. We can also reflect them in one axis, and this is not going to affect anything. So, I mean, in principle, we can ignore this fact, and I mean, this is something that we still need to pay attention when we want to quantify the error of our estimator or other things, but in practice, these things can be addressed. I just wanted to point this out because, in principle, it doesn't make sense to estimate specifically what latent position we have here, because everything is going to be equivalent up to this orthogonal matrix, right? So we can get X, let's say, some matrix in RD, or we can get X prime equals to X times W for any arbitrary orthogonal matrix, also in RD, and these two are going to generate exactly the same model. So we can basically just define an equivalent class and work with all the latent position matrices within that class. Okay, so now, going towards estimation, there's one particular way to characterize the latent positions that is useful to think about how we're going to connect spectral methods with the random dot product graph. And this is the idea of taking this matrix P. So remember that P is equal to X transpose. And we look at the eigendecomposition of this matrix. So B is a matrix of size n by d. Well, I'm assuming here that X is a full rank matrix, in which case the rank of P is equal to d, and then we have exactly the eigenvalues different from 0. So then we can factorize P with the eigendecomposition as B lambda B transpose, where B is a matrix of eigenvectors, and lambda is a matrix of eigenvalues, a diagonal matrix, and we're going to denote the eigenvalues by lambda 1 to lambda d. And I mean, we can order them from in terms of magnitude from the largest to the smallest one. So we get this representation of P, right? So among all the possible representations within this equivalent class, we can look at the particular one in which we take basically sort of like the square root of this matrix by looking at the eigenvectors times the square root of the eigenvalues. If we were working with the RDPG, the eigenvalues are all going to be positive, so this doesn't really matter too much. If we're working with the generalized RDPG, we need to take the absolute value of the eigenvalues and we need to incorporate this diagonal matrix in the middle that I talk about, but I'm going to ignore this for now. The point is that once I get this representation, if I calculate XX transpose, when lambda is positive, I'm going to recover P, and that's one particular way of representing the latent positions. Okay? So, yeah, so basically we're going to look at this particular one from the equivalence class of RDPG models. This is still not unique in the sense that you can flip the signs of the eigenvectors and you recover another eigenvector with exactly the same properties. In other cases, when the eigenvalues are repeated, we can even form linear combinations of the eigenvectors and we still get eigenvectors. So in a way, we don't really need to pay too much attention that these are just the eigenvectors. I mean, we can just work with the eigenspace of the matrix or something like that. But this allows us to characterize, or at least to restrict to a smaller class of matrices, and then this is going to connect nicely to the idea of estimating parameters in network models. But anyway, so basically we're going to look at this particular representation of the RDPG model. Okay, so now, in terms of estimation, as I mentioned at the beginning, we want methods that are efficient in the sense that we don't want to optimize over a very large space. We can think, for example, of the likelihood of an RDPG, but that would require us to solve a non-convex problem, which still, I mean, has potentially many local minima, and we wouldn't be able to explore the whole space efficiently. So instead of that, we're going to look at spectral methods. And the idea of the adjacency spectral embedding, which was defined by Sussman in 2012, I have it here. So is that we take a network A, or adjacency matrix of a network, from the RDPG model. We can write the eigendecomposition of this matrix by looking at the top D leading eigenvectors and eigenvalues, and the remaining ones. So, I mean, this is going to be sort of like a residual matrix we are not going to use. So then we look at the top leading eigenvectors and eigenvalues, and we form an estimate for the latent positions in this way. So we take B hat, the matrix of D leading eigenvectors of A, and we take lambda hat, the matrix of the, with the diagonal containing the D leading eigenvalues. We take the square root of this matrix after taking the absolute value of the eigenvalues, and then we get an estimate for the latent positions. So basically, as you can see, these two look exactly the same. The main difference is that in the previous one, we take eigenvectors and eigenvalues from the P matrix that we don't observe. And this P matrix has rank exactly equal to D. Whereas in the sample version, we observe the adjacency matrix. We look at the D leading eigenvalues and eigenvectors. In this case, this matrix is usually full rank. So, I mean, we need to truncate them. But we get an estimate for X, which we're going to call X hat, or the adjacency spectral embedding of the network. Right? So that's our estimate. Okay, so now, why do we care about the ASE and not other methods? Well, as I mentioned, this is very efficient to compute, right? We just need singular value decomposition or again decomposition of the adjacency matrix, which can be computed very fast, even for large networks. But most importantly, we have guarantees on the quality of the estimates obtained from the adjacency spectral embedding relative to the parameters of the model. As I mentioned, I'm just going to state the results here just to motivate the use of the spectral methods and focus on the methodology. But Joshua, in the next 3 lectures, is going to develop these ideas of analyzing the error in eigenvalues and eigenvectors of matrices relative to the model parameters in a deeper way. But I mean, 2 important results that motivate the use of spectral methods. On the one hand, if we look at the individual row of this matrix X hat, this corresponds to the latent position of an individual node, right? So in principle, we want this latent position to be estimated accurately. So there are results that show that the distance between the latent positions and the true latent position, xi, for every value of I, or for the largest one, in this case, we're bounding the largest distance between these two, it converges to 0 as n goes to infinity. So basically, this is telling us that when the network is getting large, we get an accurate estimate of the true latent positions of the model by looking at the adjacency spectral embedding. We have this sequence of matrix W here because of the non-identifiability that we need to take care of. But I mean, we can just ignore this W in the notation and just interpret this in the usual way that we get a consistent estimator for the latent positions of the model by looking at the adjacency spectral embedding. And another useful property, especially if we want to do inference or we want to quantify the uncertainty on the estimators, is that the rows of X hat are asymptotically normally distributed, and they satisfy some convergence in distribution like this. So basically, I mean, we have something similar to the error here, but now we look at the difference between X hat and Xi. Actually, I think this W should be on the other side, but yeah, I'll adjust that later. But anyway, so the point is that this vector that basically has the error in estimation is convergent to a normal distribution with mean 0, or in other words, X hat is convergent to X, up to some orthogonal matrix. But then we have a covariance matrix that depends on the latent position. There's not a general closed form for this matrix, but in some particular cases, we can obtain a closed form solution for this. And well, this has a square root of n here, which basically tells us that as n grows, the covariance is shrinking, so we get a more accurate estimate. But most importantly, we can quantify how much uncertainty we have on our estimate here. So for example, if we wanted to do inference comparing different latent positions or quantifying how far we are from the truth, we can use estimates of sigma and the parameters in the model, and then we can basically, for example, compare whether 2 latent positions are the same or things like that. So these 2 results allow us to do a lot of statistical inference for different problems in network data. But yeah, if you want to know more about the theory behind these results, you should come to Joshua's lectures in the next 2 weeks. So here I have stated the result for convergence of the latent positions in a more formal way. But I'm going to skip this for now. I'm going to let Joshua talk more about this. But essentially, just to illustrate the result in this theorem, which is a version stated by Atreya et al. In a survey paper on RDPG models. So for example, if we have an Erdos range graph, right? A is an Erdos range with parameters A and B. In this case, the expectation of A is equal to P, which is just this probability of the model times a matrix of ones. So the error rate for estimating these parameters basically depends on the largest expected degree, delta P here. So delta P in this case is just simply little p times n, right? Because every row has exactly the same expected degree. Or n minus 1 if you consider zeros in the diagonal, but that doesn't make a huge difference. We can also, well, this is a rank 1 matrix, so the largest eigenvalue P of capital P is just equal to P times n, and the leading eigenvector of P is equal to 1 over square root of n times the vector of all ones, right? So in this case, the latent positions of the model is in I are just square root of P divided over square root of, no, sorry, it's just square root of P, right? So in such a way that if we multiply square root of P I, square root of P times square root of P for two different latent positions, we just get P, right? So in this case, what this result is telling us is that if B hat 1 is the leading eigenvector of A, I'm going to denote it in this way, leading eigenvector of A, then what we can obtain from here is that I'm going to denote lambda hat 1 of A as the leading eigenvalue of A. In this case, x hat is just simply a square root of lambda hat 1 times b hat 1. And from here, we can obtain that the largest distance between x hat and x, which is just equal to square root of p, well, modulo some, well, we need some orthogonal matrix here. This is some constant w, and because this is orthogonal, it's either a 1 or a negative 1. So the distance, I mean, in this case, these are real numbers, right? Let me write it here more carefully. So, right, so basically here, these are real numbers, so I can just use the absolute value. So the distance between the entry I of this estimate of the latent position and the true latent position, which is the square root of p, times some matrix W, either 1 or negative 1, is going to be upper bounded by some constant. The dimension here for the Erdős-Rényi graph is just 1, because this is rank 1. The square logarithm of n divided by Pn. Well, actually, this is the L1 norm of this matrix, which is exactly the same as delta P. So this is equal to P times n. So basically, this divided by the square root of P times n. Right? So basically, the rate that we get is some logarithmic term divided by the square root of n. So that's the estimation rate for the latent positions of the model in the Erdős-Rényi case. Right? Okay. Yeah, and here I think there's a typo. This should be x hat I. So for each particular entry of this vector, or this matrix of latent positions, and xni for each particular entry as well. But anyway, so that's the result that we get applied to the Erdős ranging model. So essentially, we see here that, I mean, for p constant, for example, as n goes to infinity, the estimate of the latent positions of an Erdős ranging graph converge to the true latent positions. Okay, so now let's come back to the question that we have here, that we have a network and we want to do a statistical inference from some particular models of interest. So if we have an SVM, as we saw before, we can write the latent positions of this model using a random dot product graph, right? So in the SVM, remember the notation from last time, we have a matrix V of size k by k, which knows the probabilities of connections between and within blocks. So B RS is going to denote the probability that a node in community R and community S connect. And we have a membership matrix Z that denotes the membership. For each particular row, we're going to have a single one that is going to denote whether node I belongs to community K. So the corresponding row in this matrix, the corresponding column denoting the communities, right? And then we can write everything in this way, P equals to Z VC transpose. So if we do the eigendecomposition of B, Q lambda Q transpose, for some values of Q and lambda, basically what we can do is write the latent position model, or the RDPG model of this stochastic block model by, well, basically we take the left matrix here, Z, times the leading eigenvectors of B, or well, actually all the eigenvectors of B, Q, and then the square root of the eigenvalues. And then from here you can see easily that if you do XX transpose, you recover P as long as P is positive semi-definite. So basically, this connects the RDPG model in this side with the stochastic block model. And in particular, if two rows are in the same community, the latent positions are going to be exactly the same. So that allows us to do spectral clustering, right? So one example of the previous result, the asymptotic normality result applied to the stochastic block models is here. So this is a figure from the survey paper by Trey et al. So the idea is that if we have two communities, in principle, the true latent positions of the model, X, are only going to have two different values, right? One for one community and one for the other. And these are going to be the centers of these 2 point clouds. But then the estimates, the entries of X hat, are going to be spread around these centers. So according to the central limit theorem for the latent positions, these errors are Gaussian, and as n goes to infinity, well, these errors approach more and more the Gaussian distribution with some covariance matrix, but the covariance is also shrinking. So you can see that for larger values of n, these points, or these clusters get tighter, and it becomes easier to find the communities. So in this particular case, it may still be hard to perfectly cluster all the nodes, because you can see there's a lot of overlap between the two communities, but as n goes to infinity, the clusters become separated, and then finding the two communities becomes an easier problem. Okay, so in principle, that's good, because now we can do inference for the stochastic block model using an efficient method. We can compute the eigenvectors and eigenvalues of A. We can cluster the rows using some clustering algorithm, and there are efficient clustering algorithms for doing that. For example, the k-means algorithm. Well, in principle, this allows us to solve this problem of doing a statistical inference for some models that are not necessarily computable in the classical statistical inference setting. So now, what about extensions of the stochastic block model? Can we still do the same things for other types of models? And the answer is yes, in some cases, otherwise. I wouldn't be talking about this, but basically, let me show you here. So how can we do these connections between the RDPG and other models of interest in network data. So Keith already introduced this model before, the degree-corrected stochastic block model, with the idea being that in networks, we typically have degree heterogeneity. So people in the same community are not necessarily stochastically equivalent in the sense that some people are more popular than others, or nodes in transportation network, there are some hubs that usually receive more incoming trips or something like that. So basically, we want to be able to allow this degree heterogeneity while at the same time having some community structure. In principle, we can cluster everything by degrees, but that wouldn't be that interesting. And we want to find communities that with nodes that have somewhat similar behavior regardless of the degree parameters. So that's one of the limitations of the stochastic block model, but this was addressed by the degree-corrected stochastic block model by Carrer and Newman. So just to show you an illustration of what happens if you don't use the stochastic block model, these are two of the examples that I introduced last time. The Karate Club network that has basically two clubs that split it at some point. These are the true memberships of the Karate Club participants. But the problem here is that if you try to cluster the nodes using the stochastic block model in the usual way, what you're going to get is that nodes with high degree are going to be clustered in the same community, and nodes with low degree are going to go to the other community, right? So that's not ideal because that's not telling us much about the actual structure of the data. Here's maybe a more interesting example where we have the political blocks. I also showed you that last time. And if you remember, they are divided into liberal and conservative blocks. Ideally, we would like to recover that structure. But because the blocks are very heterogeneous in the sense that some are very popular and some are not, if we just apply the stochastic block model, we're only going to be able to recover popular blocks versus non-popular blocks. So by introducing some degree correction parameters that I'm going to show you in a minute, we are able to actually recover the communities of interest in this particular, well, in these two scenarios. Right? In the Karate Club, we're able to recover the two partitions of the network after the fight between the members. In the political blocks, we're able to recover the liberal versus conservative blocks. And that gives us a better intuition of what's happening in this data. Okay, so the degree-corrected stochastic block model is defined in the same way as the SVM. We have a matrix B that represents the connectivity between different blocks. We have a matrix Z that encodes the community assignments, but we have an additional matrix theta with n entries that denote the degree correction parameters. So if someone is more popular in the network, we can just increase the value of theta. If someone is less popular, we can make theta smaller. Then the degree-corrected stochastic block model assigns a probability for two nodes to be connected equal to a parameter B that is the same in the SVM and only depends on the community memberships, but the product of two parameters, theta I and theta j, that are proportional to the connectivities, to the popularity of these nodes. So if we have two nodes that are very popular, this probability is going to get bigger and bigger. If we have two nodes that are not so popular, then this is going to get smaller, regardless of the community memberships. So in this way, we are able to split the degree popularity versus the community affinity, which is encoded in this matrix. And well, as Gabor mentioned, we need to be careful here when we define these models, because in principle, when we define theta in an arbitrary way, these probabilities may be larger than 1. But defining it in this way makes it useful for inference, because as I'm going to show you in a minute, we can actually represent this model as a special type of random dot product graphs. So then we can also do inference of the community memberships of this degree-corrected SVM. Okay, so before talking about inference, we just need to be careful about non-identifiability. And this model is a bit more complicated than the stochastic block model, because here we have two parameters that interact with each other. We have the thetas and we have the b's. So we want to be able to distinguish whether some parts of the connectivity come from the fact that people are popular versus they come from the fact that people are in the same community or people are in different communities. So in order to do that, we need to put some constraints. The easiest one is to assume that the sum of the degrees within a given community, which basically I need to aggregate all the theta i's that are in community R, for example. This is going to be equal to the number of elements in community R, nr. Right? So in this way, we can get an interpretation of the thetas according to whether they are closer to 1, they are sort of like the average connectivity, versus larger than 1, it's people that are more popular than average, smaller than 1, less popular than average. But also a nice thing about this representation is that, well, we can link the degrees of the network. This is a quantity, I mean, we can write di as the number of nodes each node I is connected to, or basically this is the row sum of the adjacency matrix. But if we use this representation, the expected value of di is going to be equal to theta I times the sum of this quantity. And we can solve for b, and this gives us that basically the entries of b are equal to the sum of the probabilities within some particular blocks, right? So these are quantities that we don't observe. We don't observe p, we don't observe b, and we don't observe theta. But with this representation, we can obtain some plug-in estimates for b and theta, and we can do inference of these parameters if we are interested in doing that. So for example, if I plug in the adjacency matrix A here instead of the probability P, I can just take sums of blocks of the corresponding blocks in the adjacency matrix, and this is going to give me the probabilities of connection in this model. And I can do a similar thing for this. So I mean, in principle, this assumption on the thetas is going to make inference simpler. But there's still here some important issue. With the stochastic, with the degree corrected block model, we have parameters that depend on each individual, right? And if we're not very careful, we can still get some issues in which some of the communities are still going to be non-identifiable because we may have different degrees. So just to give you a very simple example, suppose that we have a network like this, and we have a group of very popular people that are all very well connected, and a group of not so popular people that are not very well connected, right? So if we're not careful, we can think of this as two different communities, which, I mean, it's a good interpretation, but in terms of the degree corrected block model, we can either fit this with two different communities, the popular one and the non-popular one, or we can simply use a single community and just be able to tell by the degrees whether there are popular and non-popular nodes. So, I mean, that creates some sort of an issue on how we are able to identify the communities. But one nice thing of the random dot product graph is that it's very natural to solve this non-identifiability once we represent everything with an RDPG. So basically, when we have the model represented as an RDPG, the only non-identifiability that we can have is this orthogonal matrix W. So if we are able to do that with the RDPG, I mean, we need to do the same thing. We need to take the model. In this case, I'm going to write P, the probability that nodes connect. So Pij is a probability that node I and node j connect. It's going to be equal to the product of some matrix theta, which is a diagonal matrix containing the degree correction parameters, the matrix Z with the memberships, the matrix B with the connectivities between and within communities, and then the same thing on the other side. Right? So basically, I can get this representation for P. And from this representation, we can also notice that P is low rank, and this can be represented with an RDPG. So basically, if I take X equal to theta Z and then some square root of B, for example, I can just take Q and lambda to the 1/2 for this. Remember that Q lambda Q transpose is the eigendecomposition of B. as long as B is positive definite, I get, again, that P is equal to XX transpose. Right? So these are the latent positions of an RDPG that is represented the degree-corrected block model. And, well, so now, one particular feature of this representation is that if we look at an individual node I, let's say a person that is in some community here, let's say community R, when you take this product, this matrix Z only contains a single one, and all the rest are non-zeros, right? So if we look at this particular row Z, it indicates whether node I belongs to community R or not. So when we take this product, basically xi is going to be equal to theta I, the degree correction parameter, times some vector that doesn't depend on I. It only depends on the community membership. Or in other words, another way to interpret this result is like saying that if we look at the degree-corrected stochastic block model represented as an RDPG, this corresponds to a setting in which the latent positions lie in different rays in RD. So here I have a pictorial representation of this. So basically, if I take the model, I calculate the latent positions in this way, and I represent the latent positions in RD. What I get is that the communities are simply going to be rays in some latent dimensional space. We can identify the communities here very easily by looking at how many different rays we have. And the degree correction parameters basically measure the magnitude of these rays. So for an individual node, if the magnitude is larger, then this is going to have a higher propensity of connecting with everyone. And then the distances between the rays, or the angles between the rays, are going to determine how likely people from different communities are going to connect, right? But yeah, so basically, with this representation, we solve the issue of non-identifiability by just saying that the model is going to be identifiable, or the communities are going to be identifiable, as long as we can identify the rays. If we have a representation in which two nodes go to the same ray, then we're going to say that they are in the same community. And that makes everything easier. Now, so one question that you may have here at this point is whether this model is realistic, right? I mean, in principle, it sounds very simple, and it sounds difficult to believe that the latent positions of some graph are going to belong just to this, to some number of rays. But actually, in practice, this happens very often. So here I have an example. This is from a data set that was collected by G et al. It has a large collection of statistics publications in different journals. There are about 80,000 publications, but out of those, there are around 40,000 authors of these publications. So from this data set, one can construct a network connecting people if they have collaborated on this one paper, right? So then we have a collaboration network with about 40,000 nodes, and zeros and one denoting whether they have written papers together. So here I have the adjacency spectral embedding of this network. So basically, I just embed the nodes of A into some latent space of dimension 3. And basically, I mean, I'm following exactly the same procedure that I described before. And what we see here is actually the same structure that is present in the degree-corrected stochastic block model. So we see 3 different rays. And in the paper, they use a different method. They didn't use the ASE, but they use something that in some sense is equivalent to it. And they discovered that these 3 rays correspond to 3 different communities in statistics. Bayesian statisticians, biostatisticians, and non-parametric statisticians. So yeah, so that sort of validates the idea that the degree-corrected block model is sort of realistic, at least for some settings, and it gives a nice interpretation of the clusters in the network. And you can also see here that if you wanted to feed a stochastic block model without degree corrections, this would cause some issues because, I mean, it's really hard to see 3 different point clouds in this network. It's better to use this ray structure in order to identify the 3 different clusters. Okay, so then this basically now raises the question on how we're going to estimate the clustering memberships on the degree-corrected block model. And so here is one idea. So taking this intuition that the latent positions lay on k different rays, we can first estimate an embedding of the network, either using the ASC or using just the eigenvectors or something like that. But now we have k different rays. In order to cluster, we need to remove the degree heterogeneity effect in some way by projecting the nodes to a point that represents all the clusters in the same point, basically. So we need to remove the degree effect in some way by normalizing or something. And once we remove that degree effect, we can cluster the rows. There are several procedures for doing that. One of the earliest ones was to just use the norm of each of the rows of X. So basically, we can take, let's say we have a degree-corrected block model with two communities. We can calculate the magnitude of these vectors and divide every point by its magnitude. So this is going to project everything into the sphere, or the circle in R2 here. And once we do that, we just need to cluster the points into two different blocks using some clustering algorithm. There are different options, either k-means or k-medians or something. But basically, once we do that, we're going to be able to identify the communities more easily. There's also another idea that has been developed for different settings called SCORE. This means spectral clustering on ratios of eigenvectors. And the idea is that instead of normalizing everything by the magnitudes of the rows, SCORE only takes the first eigenvector. For example, here I have the political block network and the two leading eigenvectors. So we take the value in the first eigenvector, and we divide the remaining eigenvectors by this value. In this case, we only have one eigenvector. So basically, the magnitude here is going to be proportional to the degree. And once we divide every point by this value on the x-axis, we take the ratio between x-axis and y-axis. This is going to project the points in one community to this side, mostly, and the points on the other community to the other side by removing the degree heterogeneity effect. And once we do that, again, we can apply some clustering algorithm, and we can discover the clusters in the degree-corrected SVM in this way. Yeah. So any questions about these SVMs or these clustering ideas in general? Okay, so that's one model. And just to generalize this idea, I'll just mention quickly this other model, the model with overlapping communities. So in many settings, it's unrealistic to assume that everybody is going to belong to the same community. Here I have an example with a network of Mexican representatives on Twitter. This is from 2018. And in this network, well, we can divide nodes by party. In Mexico, it's actually kind of hard to characterize political tendencies and parties because people usually switch parties all the time. So looking at the network is more informative in order to determine whether nodes actually belong to two different parties, or maybe a person is going to switch to another party, or they have friends in one party more than the other, or so on. And that can give us some information about different groups within the network. But what you can see here is that the true communities of the, or what so-called true communities corresponding to the parties, split the network in this way. Whereas if we fit some model that allows every node to have more than one membership at the same time, we see that some of the nodes here, colored by different, that have more than one color, actually belong to more than one group. So maybe those are people that belong to one party and then switch to another, or there are some subgroups within a given party, and so on. So I mean, in principle, this is something reasonable to expect in real networks. So in order to allow for that, we have the mixed membership stochastic block model, which basically relaxes the constraint that Z is a matrix with zeros and ones, and only a single one per row, to a mixed membership vector, such that all the entries are still going to be non-negative, but now we have the sum for each row equal to 1. So basically, this is going to quantify for node I how much the node belongs to each of the k different communities in the network. Right? And I mean, once we do that, we can define the mixed membership stochastic block model in the same way by just, well, now we cannot just look at a single entry of B because a node can belong to more than one community. But if we calculate this product, Zi, B, Zj, this is going to quantify the total amount for each pair of nodes, the interactions within a given community, and then this is going to be weighted by the probabilities that node connect in a given community of the mixed membership SVM. So basically, if you represent this as a matrix product, we have exactly the same factorization, Z, B, Z transpose, but now the main difference is that the rows of Z can be represented as vectors with more than one non-zero per row. Right, so now we can quantify which communities the node I belongs to by looking at the different, the rows that are different from 0 in this particular matrix. Okay, so now, well, there are some comments here on membership identifiability. In principle, we need that the rank of B needs to be equal to the same number of communities. Otherwise, the definition of a community becomes a little bit obscure because we can merge communities. I mean, because here, nodes are allowed to belong to more than one community. If the rank of B is not equal to K, we can merge communities and define communities I mean, a smaller model, with a smaller number of communities in the same way. So in principle, we need to assume that the rank of B is K. But the interesting fact of this model is that if we represent P, or if we represent P, like a factorization of P in this way, I mean, here we don't have degree-corrected parameters, right? So we can just remove the theta, but we get exactly the same factorization. If we represent the model as a random dot product graph, what we get is that the rows of X are now basically proportional to Z, and then some other matrix that is doing some sort of like rotation and scaling. But now these rows of Z are on a simplex. So after this rotation and scaling, we get transformations of a simplex. Here's an illustration from the GRDPG paper. So now these are the latent positions of the model, and we can see that the triangles of this simplex correspond to the communities. So if some node is closer to one of these corners, then this node is more pure in the sense that it belongs more to one of the communities and less to the others. And yeah, so by looking at this simplex, we can quantify how much each node belongs to each of the communities. There are some spectral ideas for estimating the communities in this simplex, but in general, the idea is that once we estimate the latent positions of the model, we're going to basically have some behavior like this plus some noise. But I mean, if the signal is sufficiently good, we should still be able to identify this simplex. And once we have the simplex, we need to apply some algorithm. There are different ideas proposed, for example, trying to find the corners of this simplex or trying to fit a triangle within these points or so on. And once we identify the corners, we can identify the model, and we can fit all the parameters. There are a few references here on different ideas for estimating the corners of this simplex or estimating the memberships of the model. I'm not going to go into details too much, but the idea is still the same. So once we represent the model as a random dot product graph, we can apply the same tools for estimating the latent positions, and then the problem becomes some sort of like geometrical issue of identifying corners, and we can solve things more efficiently in this way. There are some extensions for degree correction and mixed memberships together that I mentioned here, but yeah, I'm going to skip those. But I mean, the ideas are similar. It's just that now we have another parameter that is scaling every vector individually for the degree correction. But anyway. So yeah, so I mean, this is just like a brief overview of different models for network data, but there has been a lot of work in general in trying to connect ideas from a latent space model to some sort of like clustering or more general structures in random networks with the goal of identifying spectral methods that are able to do this transformation. So one can think, for example, of hierarchical community structure in the sense that maybe some of the communities can actually be subdivided into two communities. And I mean, this can be represented easily with a random dot product graph because you can think of like clusters of points in which you can actually have some subclusters. Or maybe you identify first points that are clustered in the space and then partition those clusters and so on. But there are many different ideas. Here I have some brief overview of different models for random graphs. So if you're interested in any of these ideas, you can take a look at the references. And yeah, as I mentioned, the notes are on a shared drive that will be sent to you at some point, but if not, I will upload this to my website this afternoon. Yeah, so that's a general overview. Okay, so there are a couple of other topics that I wanted to cover, but so Andresa already talked on Thursday about choosing the number of communities. So, I mean, for the interest of time, I'm just going to give a general overview. And I mean, Andresa mostly focused on likelihood approaches for choosing the number of communities, where the idea is that, I mean, in principle, we can calculate the likelihood of the network. Well, I mean, we cannot do that in practice because it's infeasible, but there are ways to approximate the likelihood, and we need to penalize for the number of communities so that we don't overfit the data. So that's what Andresa covered, and there are some references. There are other popular approaches for estimating the number of communities. One idea that is also related to spectral methods in some sense is cross-validation. So if you're familiar with cross-validation in statistics, the general point is that we split the data into two sets. One set that we use to fit the model, and another set that we use to evaluate the model without observing the data. This is a difficult problem in networks in general, because splitting a network is not that easy. Right? If we remove some edges of the network, we may create issues like making the network disconnected or arbitrarily changing the degrees of some of the nodes, which may result in a different model or other things like that. So we need to be careful with these approaches. But there are two ideas sort of based on the intuition of spectral methods that allow to perform cross-validation in network data. One idea is to split the nodes, take a subset of nodes outside. So basically, I can draw a picture here. So if we have the adjacency matrix, what we can do is select a set of nodes for training, let's say this set, and this set of nodes is going to be for test, right? So in principle, we need to observe information about these nodes if we want to fit a model that includes these nodes. So what we can do is work with a rectangular matrix. So let's say this is size n, the number of nodes, and we have n training, right? So nt is less than n, right? So we can look at this rectangular matrix. In principle, this is just a network between nodes on the training set, but we also have interactions of nodes in the training set to the test set, right? In this part of the adjacency matrix. Once we fit the model in this matrix, we can look at the set of edges in this corner here, which is basically only edges between the test and the test set. And we can evaluate our model in this area, or We can use a different loss function to calculate how good the fit of this model is. And yeah, so basically that's one of the ideas for cross-validation. In principle, spectral methods are defined by looking at the eigendecomposition of the adjacency matrix, which allows us to estimate the latent positions of the model. But we can use a similar idea here for this rectangular matrix, in which instead of looking at the eigendecomposition, this is not going to be a square, so we cannot take eigendecompositions directly, but we can look at the singular value decomposition of this rectangular matrix, and it's going to have similar properties. So we can also estimate the latent positions of the model by just looking at this part of the network without observing this area here. And once we have the latent positions, we can check whether this model fits the unobserved data well. And based on that, we can choose a number of communities, for example, or even do other things required by any sort of algorithm. There's also another idea on sampling edges of the network, but I just leave the reference here if you want to take a look later. And there are also many ideas that use specific properties of network models and either try to estimate the rank of the network, for example, using random matrix theory, and try to check whether the theoretical properties of the network satisfy the observed properties, or trying to do some sort of goodness of fit on different ways by, again, like trying to look at the model parameters and seeing whether these fit the observed features of the data well. But yeah, I'm going to skip this part, and I'll leave you some material here if you are more interested. Yeah. Okay, so in the last few minutes, I just wanted to talk about this topic of spectral embedding for multiple networks, still with the idea of trying to motivate the use of a spectral method for statistical inference in network models, but going beyond a single network and a single stochastic block model. So for this part of the talk, I'm going to assume that I have a collection of networks which have the same set of vertices or the same set of nodes representing some sort of similar units across the networks. And this is a setting that appears in many applied problems. If you think about any sort of like network data, we typically have different types of interactions between the units of the system. In social networks, for example, you may have interactions with people at work or people in your family or your friends outside of work, and these networks may look different. I mean, they may share some similarities, but at the same time, they may look different. Or even Facebook and Twitter and other types of networks, right? So these are usually called multi-layer or multiplex networks. It's a bit confusing terminology because multi-layer networks are sometimes used for more general things, but they are also used interchangeably. But I mean, this is basically networks in which we have the same set of nodes, but different interactions on each view of the network, either a layer or a different view. In other types of settings, we have networks with changing edges. For example, we observe a network at time t. We take a snapshot of the network, and then maybe we come back a day later, we observe the network again, and the edges may change. I mean, in this particular setting, I'm assuming that the nodes don't change, but the edges may change from time to time. Or the edges may regenerate every time. So for example, in an email network, the emails that you send today are going to be probably different than the emails that you sent the day before, but there will still be some similarities across the two, or across this time series. Maybe you will send emails to the same people with higher probability, and you will see edges that appear more frequently in these networks. And another example is sort of related to the classical statistics idea of having multiple observations and collecting data for these observations as features. But here, the features are networks. And in this setting, we have a very popular example, which is brain network data. In brain network data, we can represent individuals by looking at their connectivity of their brain. So basically, we take the brain of the person, we parcellate the brain into different regions, and for each person, we conduct a study to get some sort of measure of connectivity between the different regions. And this measure is going to change from person to person. There has been studies, for example, that show that there are differences in connectivity between people that have schizophrenia or Alzheimer, and one can identify which regions of the brain are more associated with this type of brain disorders. So, I mean, in general, the point here is that we have many problems in which we can look at more than one data point. We have multiple networks. But there are issues here. And I mean, some of these issues are related to the things that Cindy was talking yesterday. We have high dimensionality because typically we don't observe as many samples of networks as the number of nodes in the data. So we need models that allow us to obtain some sort of low-dimensional structure that can make inference feasible. We have also computational issues because even if we want to fit cluster to these networks in the nodes, we still need to solve some combinatorial problems, so we still need to develop some efficient ideas to find clusters in the data. And yeah, so several things. So, but yeah, so for this last few slides, I'm going to assume a model like this. So I'm going to have a collection of M networks, A1 to AM. And we're going to assume that for each network, we can calculate the expectation or the probability that two nodes connect, and this is going to be encoded with a matrix P. So now this is indexed by the network, T, going from 1 to M. You can think of T as a time or as a layer. And in principle, P can be different. So there are some challenges here. On the one hand, because we have the same set of nodes, we want to be able to extract some common information. In the brain example, for instance, everybody has the same anatomy, so the brain should look a little bit similar. If we have some clustering structure, the cluster should be similar across people, but at the same time, everybody has its own connectivity. So kids have different connectivity than adults, and ideally, we would like models that are able to characterize these differences. And another issue that appears frequently, I talked about this in graph matching a couple of lectures ago, but I mean, this also appears, for example, in time series, that there's usually dependency between the layers. Here I'm going to assume independence for simplicity, but I mean, in principle, one can allow the edges of one network to influence the edge of the other network, and that makes the problem more complicated. But anyway, and now, so once we have these models, there are in general two types of questions that we can ask. On the one hand, we may wonder about vertex properties. So if we look at the collection of networks, we may want to do community detection still, but now we have more information. So we want to be able to incorporate all of the information together in order to do clustering and get more accurate estimates because we have more data. So that's one example of inference about vertex properties, but sometimes we also want inferences about network properties. Maybe we have collections of networks. We may want to do classification because the connectivity may be useful to identify different types of brains, or maybe distinguish adults from kids and see what are the differences in their brains. So we also want models that allow us to characterize individual properties of each network and to differentiate the networks. Okay, so the simplest idea that we can think to extend the SVM to the multi-layer setting is called the multi-layer stochastic block model. And actually, this model was proposed in the same paper by Holland et al. In '83 that introduced the stochastic block model. So the idea here is that we want to keep the same communities across all the layers or across all the networks. That's why we're going to have a matrix Z denoting the memberships that is still the same. But we want each particular layer to potentially have a different connectivity. So this matrix of connectivity parameters is going to be indexed by T. Right? So maybe at time T, it could be that the network is increasing the connectivity, so we want to allow some parameters to grow, or other things. So here's just an illustration of what can we do with this model. We have networks over the same set of nodes. The communities are the same. But now, since we're changing the connectivity, we're allowing for different behaviors on each of the nodes. So for example, it could be that some of the layers or some of the time points are assortative, so network connect more with, nodes connect more with other nodes from the same group, and others are disassortative in the sense that nodes start to connect more with the other group. Or different types of behaviors by just changing the matrix B. So here, I mean, we have still the same stochastic block model. If we wanted to do inference of the communities, in principle, the first thing we can do is just take one network, feed an RDPG or do an embedding to estimate the latent positions, and look at the communities. This is going to be somewhat accurate, depending on the parameters of the network. But ideally, we would like to use the information on all the networks to do this community detection task. So here the question is, how can we construct spectral embeddings that allow us to feed the stochastic block model with multiple layers while getting advantage of having more information and at the same time having some efficient algorithms to do that. We can, for example, just try the livelihood method and maximize the livelihood, but it's still going to be infeasible to do in polynomial time. So we want to define spectral methods that allow us to do that more efficiently. And I mean, we can think of extensions of this model to other types of ideas like mixed membership or degree corrections, but I'm not going to talk about those for the interest of time. So one idea to incorporate these models together in some sort of like the same way that the RDPG is able to encode different types of clustering structure in the networks is to assume that all the layers are going to have a common principal subspace. So basically, we can factorize P in this way. We can assume that they share the same singular subspace, not necessarily the same eigenvectors, but basically the eigenvectors of each of the networks are going to be a rotation of the eigenvectors of the others. And we can allow some parameter that changes the connectivity of the networks. And this idea basically extends the SVM in the same way that the RDPG extends the SVM and incorporates other models. And it's also a special type of tensor decomposition, where if you think of the layers as, if you stack the layers together, you will get a tensor of mode 3 with n by n for the network size, and then m dimensions for the layer size. So this is sort of like a special case of low-rank Docker decomposition. But I mean, in principle, this can allow us to do inference in a more efficient way. So yeah, I'm just going to mention very quickly 3 different ideas for doing embeddings on multi-layer networks and how they connect to the stochastic block model. I mean, the simplest idea you can think of is just aggregate the layers together, right? Take a sum of all the adjacency matrices, or take the average of all the adjacency matrices, and then do an eigendecomposition of this matrix. This is actually, I mean, a very simple method and also very easy to analyze because, in principle, once you sum all the layers, because they are independent, you're going to get a matrix with somewhat similar behavior to a single network. And just looking at the eigenvectors of these adjacency matrix or the sum of the adjacency matrices, you can identify some structure on the common components. One of the potential issues here, if you look back at the examples that I show you in this slide, if you have assortative versus disassortative structure, for example, let's say if you have this network with this network, when you aggregate these two, they will cancel with each other. So that basically would not allow you to recover the signal in this layer. So, I mean, in principle, this is a simple method, and it's very good when the layers are sort of homogeneous, but it may not be useful when they are heterogeneous, like in the example I described. There are a couple of other ideas that one can use. One can aggregate the bias adjusted adjacency matrices, the square adjacency matrices. And the idea here is that once you square the adjacency matrix, you can ignore that D for now. Once you square the adjacency matrix, you're going to make this matrix positive semi-definite. And this cancellation issue of having assortative and disassortative networks wouldn't happen. So yeah, so this is another popular method for recovering common structure across multiple networks. Or alternatively, you can work with the spectral embeddings directly by looking at the eigendecomposition of this network. You take the leading eigenvectors of A, and then you look at the sum of projections. So basically, the three ideas are just aggregating different versions of the network, either aggregating A squared, or aggregating the projections. But these three different methods allow you to recover some common structure in all the layers. And at the end, what do we gain from this? Well, we have a way to extend spectral methods to the multi-layer setting. We are able to efficiently estimate embeddings and communities in multi-layer networks, and so, some of the ideas from a single network can be extended to multi-layer networks, but now we have the addition of multiple dimensions. So yeah, so I'm going to stop here for the interest of time. Joshua will continue on going deeper into spectral methods in the next few lectures. But yeah, so here there are other potential or further problems or questions in multiple network analysis if you want to check them out. And yeah, so here are the references, as I mentioned. The slides will be available soon to you, or I will upload them to my website this afternoon. So yeah, so are there any questions? Yep.
Actually, it's more maybe a general question, because you mentioned many models for graph matching and also community detection, but there are some other methods based on metric approaches. For instance, Gromov versus time distance. I don't know if you heard about it. And I would like to know how these methods are compared to the ones that you presented. And I'm not sure if it's possible to get some statistical properties of this kind of methods. Are they used, or, I mean, can we say some stuff about the quick recovery on this kind of methods?
Yeah, so for example, for Gromov-Wasser times distances, I think in graph matching, they are used to match point clouds rather than specific vertices. So I'm not very familiar with that model for network data, but yeah, I've seen some results on matching with this type of models. But the idea is slightly different in the sense that, I mean, we don't necessarily have node correspondences, or I mean, they can be defined, but now the correspondences are between point clouds rather than vertices defined in a joint model for network data. But yeah, I mean, there are some ideas based on that, but actually, I think they have been used for correlated errors ranging models as well, but I'm not aware of any results that relate the method with the correlated errors ranging model. But
do you think it's possible to make this kind of statistical inference on these methods, or some other methods like that use purely machine learning to cluster graphs?
yeah, I mean, it's possible, but I mean, depending on the method, there are issues. For example, computational issues. Some of those require to solve non-convex problems, for example. But yeah, I mean, I guess depending on the specific model, there may be some connections. Yeah, we can talk more about that offline if you want. Yep.
What is the complexity of fitting a spectral method, like time and memory complexity?
So, well, the complexity basically depends on the number of nodes and the sparsity of the network. So, one way of fitting this is, for example, using power iteration, which has complexity about n times d, where d is the average degree of the network. So yeah, I mean, in principle, if the network is sparse, you can fit these models very efficiently and for very large networks.
But these models are dense, like our latent space models and our UPGs dense.
what do you mean by dense?
I mean, like the largest component, maybe the size.
Oh, okay, so, well, I mean, that depends on the specific parameters that you have for your model, so let me go back here. Well, actually, I talked about that last time with exact recovery. So, I mean, depending on the parameters, as long as the average connectivity is of the order log n over n, you get a connected network, and it's like greater than 1 over n, you have a large component. But yeah, well, I mean, you can adjust the parameters to generate different densities in the RDPG.
One final question. You assumed D fixed, right?
Right.
But I think Keith mentioned that you might be able to estimate D using the spectral gap, something like that, right?
Right, yeah.
But if you need to choose both D, estimate both D and the number of blocks, number of communities, you first estimate the dimension, then the number of blocks.
Yeah, that's a great question. So I guess it depends on the approach you use. I mean, some approaches don't require you to estimate D, especially if you use the likelihood, you don't necessarily need to think about the RDPG and you don't have to estimate D. But if you think about fitting an RDPG first and then fitting a number of communities, yeah, you need to first figure out what's your embedding dimension, and then the number of communities and the number of dimensions can be different. So yeah, I mean, in principle, it depends on the approach you follow. Any other questions?
Okay, let's thank you.
Thank you.